We now turn to RI-LTA, namely Random Intercept LTA, with an emphasis on the multi-step aspect of that. Slide 70 shows an example of RI-LTA with 3 time points, C1, C2, and C3, where we have distal outcomes Y influenced by the last time point, the latent class variable C3. The new feature here is that we have a continuous latent variable F, which we think of as a latent trait or a random intercept. It's a time invariant variable varying across subjects, so it is a between subject construct. Each indicator is influenced by this trait, and the remainder in the indicator is influenced by the latent class variable, where the latent class variable captures the within subject variation across time. So that's similar to random intercept cross-like panel modeling, RI-CLPM. The indicators at a certain time point have different loadings on the trait factor, and those loadings are held equal across time. So U1 loading is equal to U7 equal to U13, etc. This means that for each indicator, the correlation due to the trait is constant over time, which is the hallmark of a random intercept factor. This factor F can also be influenced by the X covariates. Both are time invariant, varying between persons. The X is between persons, and so does the F factor. We didn't draw those arrows because it made the picture look messy. This is described in the paper from 2022 in Psychological Methods, and also in Webtalk 1, where I go through several different data sets to show that RI-LTA often fits data better than regular LTA. I should also say that 3 time points is the minimum for RI-LTA. You can fit models for 2 time points, but you would need very large sample sizes like 4,000 or 5,000, so it's not practical. Now turning to multi-step approaches, in this case the measurement model is this whole upper part of the model, all time points including F and including C on C for the latent class variables. So in this case you cannot estimate time-specific LCAs because you also have that influence from the factor F. So for instance, for BCH weights you cannot do time-specific LCAs to create the product of the weights. So you would have to compute the weights for all time points together. And in fact, this also makes 3-step awkward, where load just must be computed manually. We're going to take a look at BCH and 2-step approaches for RI-LTA. Now, regarding multi-step approaches to RI-LTA, relatively little has been done to date. We have WebNote 21, where Tiemer did some simulations for both covariates and distal outcomes. For covariates, he found that 2-step does better than BCH. And for distal outcomes, he found that BCH does better than 2-step when distals are non-normal within class. So that issue comes back that we discussed before. Now we're going to focus on multi-step RI-LTA with distal outcomes, so only distal outcomes, no axis for simplicity. And they are normal within class as per how we generated the data. And we're going to look at BCH and 2-step. On slide 72 then you have the input for RI-LTA, first step of BCH. So you have a new data set here with the 18 indicators, and we have 3 Ys. We also have X, but we're going to ignore that for now. And in the first step we use the latent class indicators, the 18 of them, and they're a binary. And we have 3 latent class variables, and we want to save the Ys, the distal outcomes Y, for the second last step of BCH. And what's new here then is that we have to have an algorithm equals integration statement in the analysis command. And that's because we're defining this factor f, this continuous latent variable, measured by the indicators at each of the 3 time points. And here's how we hold the loadings equal across time by these labels. And we use an asterisk here for the first set to free up u1, which would otherwise be fixed to 1 as the default. Instead, we set the metric in f. The variance of f is 1, set the mean to 0. And in BCH, for RI-LTA, we recommend that you do have C on C. You do include C on C, so C2 on C1 and C3 on C2. And that's discussed that's per analysis in web note 21. The rest is similar then. You have model C1, model C2, and on the next slide, model C3, where you have measurement invariance across time. Going to the next slide, continuing here for the third latent class variable. And then you save the BCH weights, and we put that in a new data file. Well, here's the last step of BCH. You have this new data set, and we're going to have use variables y1 through y3 here. That's all we work with for BCH. And the first 2 are categorical. And we have the training statement here. And since it's 3 variables, three latent class variables with 3 categories each, we have 27 weights. 3 times 3 times 3, BCH. And look at this now. We don't have any f by u statement here because the u's are not included in the model, as you see on the use variable list. The information from the use is carried by the training variables. So no f by u, and therefore no algorithm equals integration is needed. F starts at equals 0 as usual. And you have C on C here in the model. And now for model C3, last time point, you allow the thresholds and the mean for Y3 to be different across the classes. So having C3 influence Y. Slide 75, we turn to the first step of 2-step. And here, as often with 2-step, you can go back to the original data because there's no save data of interest really. You don't save C probs, you don't save BCH weights. So again, first step, you have the 18 latent class indicators, 3 latent class variables, and you have algorithm equals integration because you have f by u, and as we recommend, you have C on C. For model C1, C2, and C3, you have measurement invariance here. And this starting value can be ignored, left over from a simulation, but you have S values here. Turning to slide 76, we look at the last step of 2-step, where again we start from the original data. And the use variable list is then including not only the distal outcomes but also the indicators, the 18 indicators, because we fixed the measurement parameters of those indicators. So we need algorithm equals integration again, and from the saved S values at the in the output of the first step of 2-step, you get this list of variables, and you get the C information from the first step, also fixed, and the F by fixed values here. And on slide 78, you get the fixed measurement parameters for the U indicators for model C1, model C2, and on slide 79, model C3. And here for model C3, you see the distal outcomes coming into the picture, the thresholds and the mean for the Y1, Y2, and Y3, and continuing to slide 80 for the last class of C3.